Alright, so we're going to be talking about Markov decision processes. And just to start with a brief outline, we're going to start by talking about deterministic environments. Then we're going to move into stochastic environments. Then we'll talk about finally what we're here for, Markov decision processes. And then we'll look at utility over time. And then finally we'll look at this funny looking pi star, which is really just to represent the optimal policy. So with that said, we're going to start with the deterministic environment. And this is the environment we're going to be looking at for the entire presentation. And it's a 4x3 grid. And what you can see is the reward for each state, and that is negative 0.04. And then there's these two states to the right, which represent the terminating states. So our agent has a pathfinding task right now. And they want to take a path that will result in their highest reward and that will end in a terminating state. But remember, the key thing is the highest reward. So looking at this, you can see there are going to be two optimal paths possible for it to take. The first path is where it's just going to go up, up, right, 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 and get to that +1. And the second is going to be right, right, up, and then right, and also get to that +1. And you also note there's a little bit more risk because it's closer to this -1, but we're deterministic, so we're not actually concerned by that. But what if we are in a different scenario where every single reward for the states were greater than 0? And so what we find here is that the goal of our agent is to maximize its reward. So what you're going to find here is that the agent is actually never going to go to the +1 or -1 terminating states. It's in its best interest to continue to maximize its reward. So what you see here is this agent is actually going to move everywhere except this +1 and -1, because that's how it can get a maximum reward, in which case this will just go to an infinity reward. So what if instead of having an environment where everything we expected to happen happened, instead we had an environment with stochastic, meaning there was some randomness in it? And so the way we're going to do this is we're going to say the agent can choose the up direction. And what's going to happen actually is there's going to be some kind of change. So it's going to become a probability distribution where there's an 80% chance that the direction they chose will be the one that's actually executed. But there's a 20% chance that the direction they choose is actually going to not be selected, and the direction clockwise to their direction is going to be chosen. So that in this case, they're going to go right instead of up. In the next case, we're still following this clockwise direction. So you'll see 80% chance of what they chose, but a 20% chance of the clockwise direction. So that's our stochastic environment. And now what we want to do is we want to formalize this by framing it as a Markov decision process. But we want to first understand what a Markov decision process is. So it's made up of 4 things. And the first thing is that every Markov decision has a set of states S. It also contains a set of actions, which is given by a state S. So you can see there's this A given the argument of S, and that's going to return the set of arguments, or the set of actions possible given the state. And if you recall from our past example, you'll notice that at the bottom left, there was a possible move to the left and down. And this may not be possible in some environments. In our environment, we allow it, because we want the ability for them to bump against walls. But in other environments, it may not be possible. And this is all to say that every state does not guarantee the same set of actions in a Markov decision process. Next, we have a transition model P, which receives a state S and an action A. And we have this P of S prime given SA. And basically what this is saying is the probability of this new state given the state and the action. So in our past example of a stochastic environment, what you see here is that there's going to be 2 possible state S primes that we could deal with. The first of which is when the action we chose is the one that's actually executed, and that's going to have an 80% probability. And the other case is where we don't get what we selected, and that's going to have a 20% probability. And then finally we have a reward function R, which receives a state, and then we have R of S. Now we already implicitly showed how this could be implemented because we had that matrix with all the rewards already built into it. So that's one way you could go about it. So with that, we now have this environment, and we want to create an agent that can successfully play through this stochastic environment. And so to do that, we need something called a policy. And a policy specifies what an agent should do for any possible state in the environment. And we refer to this as pi. So the way this works is we call pi with the argument of s, and it will output some action A. And then there's another kind of policy which is called a complete policy. And this is one that can always perform the action regardless of the result of a past action. Essentially saying that this is a policy that is never going to get stuck, which is obviously a very desirable quality to have for your policies. But another part that we really want is not just a policy, but a policy that, if not optimal, is very good. So an optimal policy, also referred to as pi star, is always going to yield the highest expected utility. And we're going to define that in a little bit. But essentially we still have the same behavior of pi star s is going to output some action A, except in this case that A will yield the highest expected utility. So with that, before we start defining expected utility, we're just going to look at what an optimal agent would do. So in this example, again, we have this greater than or 0. And we also have our terminating states, +1 and -1, and our agent is again starting at the bottom left. So what we're going to find in this case is the agent is going to follow the same behavior we saw in the deterministic environment, but there's going to be two differences. The agent cannot move towards this, so you'll see it instead moves to the left, which could result in a plus in moving up here, but that still guarantees it doesn't go here. The same behavior is here, so we're still not going to hit this -1. And then we also have this down arrow, which is going to guarantee that it cannot hit the -1. So that's how we're going to behave if we're in a situation where an infinite reward is possible. But now we're going to look at pretty much the opposite scenario, and this is where we have something very negative for our rewards. And so what you're going to find here is that the agent's goal is now to maximize its likelihood of just getting to a terminating state. And as you can see here, all it's trying to do is just get to this -1 or +1 as fast as possible. That's why this goes left, up, left, up. All it cares about is just getting to a terminating state as fast as possible when you've given it a very low reward. It doesn't care about the intermediary steps, it just wants to get to the end. But now we're looking at the opposite issue of having extremely low rewards, and now we're looking at the issue of rewards that are so not damaging that it's in its benefit to really scope out for this +1. And so this is kind of a very conservative agent. So to walk you through it, you can see its primary goal is to get to the +1. If it reaches the 20% chance of going to the right, you can see it will always try to go back this way, but there's a 20% chance of going up, but that's just going to bump it to go back into the state. So we're guaranteed to get to here. And again, you'll see we go here, 80% this way, 20% this way. So we're eventually always going to get to the +1 when we have the rewards that are not super damaging. And lastly, we're going to look at our original example of -0.04. And you'll notice that this is not in the range that I gave for the previous example. And so what you find for the result of this is that the agent is now still has the same goal that we saw before. This guarantees that we take this path, but once it gets to this state here, it's now, you can see, taking a risk. What it's now doing is it's saying, I want to get up to get to the +1, but I'll also take the -1 because I'm trying to maximize my expected utility, which is basically to say not a single goal, but a more long-term approach over multiple approaches. So that's how the -0.04 is going to look. And now we can look at utility over time and how we're actually going to be calculating it. And to first kind of formulate this, we have to understand what a finite or an infinite horizon is. And to start, we're going to look at an infinite horizon, which is where there's no limit on the number of steps an agent can take in the environment. And this is what we've been looking at for this entire presentation so far, where the agent can take as many steps as it wants. And so what this yields is an optimal policy is stationary, or it's unchanging. And that basically is meant to say that there's no reason that the optimal policy has to change at any point during the run of the agent. Which then takes us to the finite horizon. And the finite horizon is where there's a limited number of steps, say like 100 for example, that an agent can take in the environment. And what this is going to yield is that the optimal policy is actually going to have to change depending on which step the agent is on, which is why we call this optimal policy non-stationary. And the reason why this is the case is that an agent that is not reaching the terminating state in a finite horizon is not a successful agent. So it can no longer just maximize its reward to infinity, it has to reach that ending state, which is why as the game continues, it becomes more and more important for the agent to approach the terminating state, so at the end it can reach the terminating state, if not before the end. So with that, we're now going to look at how we can calculate utility. And up until this point, this is what we've been doing, an additive approach. And this is our utility function, where it's receiving a list of all the states we've been in, and all we're doing is adding them up. And this is what leads to the infinite reward, where essentially this is just going to be a straight line going up. So this is clearly going to be a problem. And the solution to this is something called a discounted reward. So you can see here we're still receiving that list of states, but what we've added, and we're still summing, but what we've added is this gamma to the power of I, and we define gamma as a number between 0 and 1. So if we set gamma to 1, then what you find is that we just have the additive utility that we just discussed. But if it's not, this gamma is going to progressively make the reward smaller and smaller, which is going to make it, in the infinite horizon situation, more and more valuable to reach a terminating state because the agent isn't getting any reward at this point. So that's what this is trying to solve, and it also makes it a little bit smarter overall. So now with that, we can look at expected state utility. Basically, what is the expected utility of every single state? And this is really powerful because with infinite horizons and discounted utility, the optimal policy is actually independent of the starting sequence, meaning it's actually to our benefit to calculate the utility of each state as opposed to looking at the sequence. So we can calculate that, and then we don't need the sequence. And that means that R is now going to be seen as a short-term reward, and U is going to be a long-term reward. But the question is, how do we calculate this U for a given state? And I'm going to show you one potential solution. It is not the best solution. It is computationally very intense once you move on to larger problems. So this is definitely not the best solution out there, and there's a lot of really good work going on that you're more than welcome to take a look at. But to start, let's look at the Bellman equation. And so the way we define the Bellman equation is we have this U given some state. We are going to get the reward of that state and plus this gamma, which we already talked about, the discount. And we're going to get the max value of this function for every single viable action. And what we're doing is for every single possible state the action provides us, this action and state provides us, we're going to multiply the probability of this S prime occurring by the utility of that S prime. And so whatever best action comes out, we're going to multiply it by that gamma, and that's going to be the utility of this state. But you can probably tell there's a problem with this, and that's that this U is actually going to S prime, but at no point do we actually have a base case. Now, if we filled in U with states beforehand, that would be a different case. But we haven't done that, so we need to do something to fix this. And what we can do is something called value iteration. And what this basically means is we're going to add a limit to the recursion. So we have our base case now, which is U of 1 is of the state is equal to the reward of that state. And now we can make it so we have this utility of K, which is just some number greater than or equal to 1. And then we have the same exact equation, as you can see. The only difference, though, is now we're decrementing that K by 1. And the result is that the larger the K, the more long-term focused this utility is going to be. But it also means that we're going to be doing more and more calculations. So just to put this in perspective, imagine we have a scenario where we have 10 actions we can take, and for every one of those actions, there are 10 new possible S primes that we're going to have to examine here. What that means is we're going to see exponential growth. So the first step, if U of 1, we'll just see 10. But then we're going to start to see 100, 1,000, 10,000, 100,000, a million. And that's just looking at 5. And so what you see is that this clearly has some problems that needs to be addressed through cleverer work, but it is a really nice starting point to understanding Markov decision processes. So now we have a utility function that we can use for the grid world we just described. And so now we can look at how we could actually compute pi star, our optimal policy. And so the way we do this is we get the argmax, and basically that's just max, except now we're returning this a instead of the result of this. And what we're doing is we're just returning the probability times that u of s prime for each possible one, and whichever action we're happiest with, we're going to return, and that's going to yield the highest expected utility. So when we look at this, if we have a high enough k, we're going to end up with a result like this. You can see we have this gamma is equal to 1, and we're using an r for each state is equal to negative 0.04. And if you recall, this is following the same pattern. We're just going to follow the maximum likely estimate, really. So if we're in this state, for example, we could either go right or we could go left. And you can see this has a higher expected utility, so we're going to follow this. We'll follow this, follow this, follow this. And then obviously from here, we're going to go to this plus 1 instead of this 0.660. And so, and when we're at 0.660, we're going to go to 0.918 instead of this negative 1. So that's kind of a visualization of how this pi star is being used. There are a lot better policies, and we're going to be looking at more later on. But this is just a brief introduction to Markov decision processes. And yeah, I hope this was helpful. If you have any questions, feel free to send them to me. And hopefully I didn't talk too fast. Thanks.